This is the first 9.2 video where we're going to learn how to conduct a significance test about a population proportion. So a significance test, if you remember from the previous videos, we said Coach Reedy claimed to be an 80% free throw shooter. And so we had our null hypothesis that P, the proportion of free throws that he made in the long run, was 80%, but we believe he's lying. We don't think he's an 80% free throw shooter. So we have an alternative where P is less than 80%. So after he took 50 shots, we have an SRS of 50 shots where he made 32. So we get a sample proportion of 64%. It's much lower than what he claimed. So we have evidence for the alternative, but how strong is the evidence? So P again represents the actual proportion of free throws that Coach Reedy makes in the long run. So the thing about a significance test is we have to assume the null is true until proven untrue. It's kind of like a courtroom where the person is innocent until proven guilty. And that's exactly how we approach all significance tests. So we have to assume that he is an 80% free throw shooter until we have evidence showing that he's not. So in order to prove that he is not an 80% free throw shooter, we have to assume he is an 80% free throw shooter and show that his sample would rarely occur by chance if he actually was an 80% free throw shooter. So the first step to a significance test is assume that the null hypothesis is true and consider the sampling distribution of p hat. So if he was an 80% free throw shooter, what types of proportions would we expect to occur in simple random samples of size 50? So the sampling distribution of p hat, if he was an 80% free throw shooter, should be centered at 80%. And then we can check the other conditions to see if the shape will be normal and what the expected variability or spread is. The shape of the sampling distribution of p hat, assuming he is an 80% free throw shooter, will be normal because of the large counts condition. The sample size is 50, so we expect 40 successes and 10 failures. Both of those are greater than or equal to 10, which means the sampling distribution of p hat will be approximately normal. The center of the distribution will be equal to whatever the population parameter is, which in this case, we're assuming is 80%. So you can see the mean of the sampling distribution of p hat is equal to, and this is p naught, this is the null. This is how I symbolize the null hypothesis, which is 80%. So you can see this is actually what the distribution looks like here. It's a sampling distribution of p hat, assuming that the population parameter is 80% and it is approximately normal with a center of 80%. And then finally, once we check the 10% condition, we can figure out what the spread would be for this distribution as well. You should remember the formula for the spread or standard deviation of a sampling distribution is p times 1 minus p divided by the sample size. And so we use the null for this, and we get a standard deviation of p hat of 0.0566. So just to refresh on what a sampling distribution is, it's the distribution of all possible samples of size 50. So if Coach Reedy shot all his shots possible and we randomly selected samples of size 50 and plotted the proportion of each of those, that's what this sampling distribution is. So this is basically the expected proportion of made free throws in all samples of size 50. So that's why I kind of started drawing these just to refresh on this is multiple samples, all possible samples that can be taken. And so when we think about this, we think, well, we'd expect it to be 80, and there's this amount of spread here of expected variation. So what's the probability that he shoots 50 shots and he makes 64%? Well, now that we know it's centered here and the spread is here, we can calculate that probability. We can find the probability of p hat being 64% or smaller from this distribution. And that value is our p-value. So a p-value is the probability of your sample or that sample occurring, assuming that the null is true. So what we did is we used a sampling distribution, assuming the null is true, and we calculated the probability of this p hat occurring. So we did lower from negative infinity up to 0.64, because that's the p hat that we had with the mean of 80 and a standard deviation of 0.0566, and that probability is 0.0023. So there is a very, very small chance, or a very, very small probability of him making 64% of 50 free throws, assuming that he was an 80% free throw shooter. So what we're starting to think is he must not be an 80% free throw shooter. This distribution must not be centered at 80. It must be shifted lower to 70 or 60, or we can't determine where it is. But what we can say is that with this small probability, we don't believe this to be true. So we're going to reject it. Now, the next thing you need to learn, though, is College Board and our textbook, they want you to know what a test, and I want you to know what a test statistic is. So instead of calculating the p-value like this, what they do is they find the z-score of this p hat. So think about how to find the z-score. You do the observation, so 64 minus the mean of 80% divided by the standard deviation. And that gives you the z-score of this value. The standardized test statistic, and it's standardized because it's the z-score. The standardized test statistic is the observation minus the mean of the distribution, which in this case is the null, divided by the standard deviation. And so we get a z-score of negative 2.83, which we should know right now that a z-score of negative 2.83 is very far below the mean. So we should know that it's going to be a very rare occurrence to get that z-score because of the 68, 95, 99.7 rule. And so what we do with the test statistic is we use this value to actually calculate the probability, or the p-value, which we know the p-value we've already calculated is 0.0023. But since we're going to be required to calculate the standardized test statistic, I'm going to teach you to calculate the standardized test statistic first and then calculate the p-value. So if we were to use the standardized score to find the p-value, now we're going to use normal CDF from negative infinity to here with a mean of 0 and a standard deviation of 1. The standardized test statistic, again, it's the probability of getting a z-score, or I'm sorry, the standardized test statistic is the z-score. And to find the p-value, we use that and plug it in from our negative infinity up to the negative 2.83, the mean of 0 and a standard deviation of 1, because it's coming from a standard normal curve. And you see we get the exact same probability that we found earlier. The last way you can use the test statistic to find the probability, or the p-value, is using table A. And so I'll run through that real quick with you on table A, just as a refresher, in case it's mentioned somewhere along the future for you. To find table A, it's in the formula chart for AP Stats, which is on Canvas. You scroll down to, I think it's the third page. Here is table A, and it shows the probabilities to the left of every z-score. So our z-score was negative 2.83. So if I go to negative 2.8 right here, here's negative 2.80, negative 2.81, to here is the z-score for, or the probability of less than or equal to negative 2.83. And you can see there's the 3 and the 8. So these are all the negative z-scores on this part of the table. You can see they're all negative here. And if you scroll on to the next page, it gives you the probability to the left of all of the positive z-scores. You will never need to use this. You can always just use normal CDF in the calculator. Just wanted to make sure I had it in here as a refresher. If they reference table A, this is the table of values they're talking about. So these are the last values that you need in order to run a test. You just need to have a p-value, and then you can draw your conclusion based on your alpha level. But I wanted to give you an understanding of where this p-value comes from and what the standardized test statistic is. So moving forward, in order to run a test, we are going to have to check the conditions to make sure the sampling distribution is normal. But when you're checking the conditions, you're always going to be assuming that the null is true. So the random condition, we've done that a million times. 10% when you're sampling without replacement. We have to make sure our sample is less than 10%. The large counts condition now, we're assuming the null is true. So we'll do the sample size times whatever the null is, and the sample size times 1 minus whatever the null is. They both have to be greater than or equal to 10. And the standardized test statistic, the simple formula is it's the statistic you have minus the null parameter divided by the standard deviation, just like we saw here. Later in the video, you'll see a specific formula for tests about population proportions.